We think in this one comment on a theorem or observation in group action. So group action is a homomorphism from a group to its group of symmetries. And we can look at this thing that, okay, let's say we have a group G and set X. Then for any element of the group and any element of the set X on which the group acts, we have that we can define Gx like a product. Here we can put some operation symbol, but let's for simplicity choose to just give it an empty symbol, just writing as multiplication. So this is the action of element lowercase g on element lowercase x from X. From the group G's elements is the lowercase g. And now let's state what we'll sort of prove. So this is a group action if and only if there's these two conditions satisfied, which are sort of very important conditions for group actions. So any two elements from G and any element on which the group G acts, we have the following two things. First of all, there's this sort of associativity between the group's elements and the element of the set on which it acts, and also the identity of the group will keep the element from X also. Alright, whether I put a dot there or not, it doesn't matter, I mean the same thing, alright? So interaction between the elements by the same operation, underlying operation everywhere. Alright, well, so now let's see. Is this actually true? So I mean, is it a group action if and only if these two things are satisfied? Well, we want the group action to be, it should be a homomorphism from G to its group of symmetries of the elements there. Well, let's use this, and I'll consider H to be G inverse. So we do have that G times G inverse X like this is actually equal to EX, and that should be equal to X. So using these two conditions, Ex is X and this is associative and this is identity, of course, we get this, but we can also switch, we can say G inverse times G times X. Alright, this is again E times X is again X. And so we have this sort of mapping for every X, or actually for every G inside the group, we have this mapping X goes to Gx, which defines a homomorphism. It defines a homomorphism from G to its group of symmetries, and that proves the statement.